Uh, okay, we talked about nodes and meshes and everything. Now we are going to talk about some fundamental quantities in electrical engineering. The first one is the most fundamental, probably quantity in electrical engineering, which is electric charge. Now, you know, electric charge is a fundamental property of matter, actually. So we use the symbols Q, the capital Q or the lowercase q. Not 100%, not all the time, but usually the capital is used for constant charge and the lowercase is used for the times when we want to introduce charge as a time-dependent variable. Okay? For example, Q of t. The unit is coulomb or C. And as you know, charge is quantized, meaning that you cannot have charge less than charge of an electron. So charge is a multiple, is an integer multiple of the charge of electron, which is 1.602 times 10 to the negative 19. But for electrical engineering, something much more important than charge is considered, which is electric current. We usually use I, the capital, or lowercase, depending on the context, and sometimes depending on whether we want to introduce current as a time-dependent variable or time-independent variable. How do we define current? Current is the rate of change of electrical charge or electric charge. Well, in other words, more textbook definition is the rate at which charge flows through a conductor, okay? So because we're talking about rate, it's obvious that we're gonna have a derivative of Q, or derivative of charge as a definition for current. Now, unlike charge, current has both magnitude and direction, okay? And you're going to see in many circuits that we can have current flowing in either direction. One very important thing is that for historical reason, we assume current follows the direction of movement of positive charge, okay? Many of you already know that this, the positive charge inside matter usually is not moving. That's the negative charge, electrons that are moving. But for historical reason, because people initially thought that those are the positive charges that move. So just to respect that, we consider the direction of current as the direction of movement of positive charge, which states that current is actually the opposite direction of the movement of electrons. Okay? Does it make sense? Only for historical reasons. The units of current is amps, and this is something that I want you to start making yourself comfortable with. Finding the units of different quantities. For example, we know that the units of current is amperes, or shown with the letter A, capital A. Can you give me another units of current based on the equation given to you? Sorry? Yeah, exactly. Do you see the equation? What's the equation of the numerator? Coulomb. What's the unit of denominator? Second, okay? So Coulomb per second is equivalent to amps. Okay? Now, let's do an example on this and see where we're at. So, an expression is given to you for Q, for electric charge, which is a multi-expression. and they are asking us to plot Q and I. Let's first plot Q, which is given to us. So for negative time, what's the value of charge? Two coulomb. So it's a constant value, right? And this is 2 coulomb. How about for positive time? How should I plot this? What's the function like? It's an exponential function. How do you plot an exponential function? You cannot exactly plot it, right? Because it's not a line, it's a curve. So how do you approximately plot an exponential? You need to do two things. Okay, first, plug the value at the start of the interval. The start of the interval is 0, right? Plug 0 to that equation and tell me what's the value. What is e to the power of 0? 1, okay? So it's going to be 5 minus 3, right? 2. So the starting point is 2, exactly like the value that is on the plot. What happens if t approaches infinity? Do it like this. A very big number, positive big number, right? Look at the exponent. Negative 50 times a very positive big number. It's a very big negative number, right? And what is e to the power of a very big negative number? How do you handle negative exponent? 1 over positive exponent, right? 1 over e to the power of a very large positive number. What's that? 0, okay? I want you to remember that. E to the power of a very big negative number is 0, okay? So the exponent term goes to 0. What's left with, what you're left with is 5. Right? Okay. That is Q. Any problem with that? This is probably the single most important function in this course, exponential. So start, if you're not already comfortable with it, you should practice more. Now, how can I find current based on the expression given to me for charge? This one. Take the derivative, time derivative of Q. Let's do that. So I is equal to dq over dt. What is the value of current for negative time? What's the derivative of the expression for negative values of time? 0, right? Because that's the constant. 0 amps. For positive, it has two terms, right? The constant 5, which gives out the derivative of 0. How about the second one? I brought this formula for you from your math courses. How do you take the derivative of e to the power of at? You bring the coefficient of the exponent behind the function and repeat the function. So a in that case is negative 50 times negative 3 is 150. E to the negative 50t coulomb for t positive. Any problem? Sorry? Yes, thank you. Okay. So let's plot this. What's the current for negative value of time? 0. How can I handle it for positive value of time? 2 points. Remember, start of the interval when it approaches infinity. The start of the interval is what value? Which value? 0, right? Plug in 0. What's the value of the current? 150. If t goes to infinity, what happens to the exponential? Goes to 0, right? It dies. Okay. Any problem with this? Now, you only need the final result of this, but I'm going to walk you through the process of finding this so you know where it is coming from. You won't need it for exam or something, but it's good to know. So this is the equation that we initially had, right? This is the basic definition of current based on electric charge. What have I done here? Just multiply both sides by dt. So nothing is strange here. Right? Multiply both sides by dt. That is what you get. Now, because both sides include some differentials, we can integrate it, right? The only thing that you have to pay attention is that the right-hand side has the differential of time, the left-hand side has the differential of charge, right? So if you integrate it, the bounds of integral should be consistent. So the left-hand side should be integrated over q, the right-hand side should be integrated over time. Am I making sense to everyone? So the left-hand side, I've integrated from two just arbitrary numbers, from qt naught, t0, to qt, and the right-hand side from t naught or t0 to t. And one thing, anyone interested or anyone being confused by the t prime inside the integral? You're familiar with this notation or no? Do you know why I chose to change t to t prime inside the integral? They never explained that to you in your math courses? No? Okay. Very quick notes on the side just to hopefully clear the confusion. If that is f of x, what is f of apple? What is it? Apple squared plus 1, right? So does it matter which variable I'm using inside the integral? It doesn't matter. I can use t prime, I can use tau, I can use apple. So why do I need to change t to t prime? Because if you look at the bounds of the integral, the upper bound, it's t, right? The one inside the integral is a variable of integration, which is changing. But the t at the upper bound is some number that you plug in. So I just want to discriminate between them. I want to tell you that these two are different. I may use tau, I may use x, I may use t prime, okay? So nothing to be worried about. I've seen many people use t, okay? It's not exactly right, but I mean, many people do it too, okay? Did that clear things up, okay? So it's nothing to worry about. Is it a cherry or an apple, whatever that is? Okay, so I write my integral, and then what is the integral of dq? What is the integral of dx? X. So the integral of dq is q from the upper bound minus the lower bound. So qt minus qt naught, right? Right hand side, just write it itself, whatever that is. So up to this point, I hope that you could follow me, right? Now just take the qt naught to the right hand side and you'll have the final equation. And I'm going to explain what it means. So look at the first purple box, highlighted box. Left hand, top left, okay? When is that equation useful? When you have q, you want to find I, okay? What is this red one used for? When you have I, you want to find q. And the idea of derivative and integration makes sense because you're doing it backward. Whatever you did, you took the derivative, so it should be backward. You should take the integral, right? So what is the single probably important difference that stands out comparing these two equations? In order to do the first one, you don't need any extra information. But in order to do this red one, you need one piece of extra information. What is that? What do we call that? Charge at the time, at the starting time. Not exactly time 0, t naught. Okay, it could be 0, it could be 5 seconds, whatever. What do we call that? We call that initial condition. Okay? You had it in almost every integral that you dealt with, right? What's the integral of x? 1/2 x squared plus c. What does that mean? It means that whether c is 0 or 10 or 1000, it will give you the same derivative. Same reason we should have some initial charge. Otherwise, we cannot find the final answer. Okay? So remember this. This is initial charge or initial value for charge. Any problem understanding the equation? Initial charge at t equals t0 or t naught. Okay. Now, if q of 0 is 0, find q of t for positive time. First of all, tell me what is t0 for this specific example. 0, right? This is t0. Okay. Now, this is a piecewise plot given to us for I. Should I use the derivative or should I use the integral? The integral. First of all, I is given to us. And second of all, it's sort of a hint in the statement of the problem. You have some initial value which suggests using an integral, okay? So let's do it. How do you suggest I do it? We have to find current, we have to find charge for t greater than 0? Zero to 6?
0 to 2 plus 2 to 4 plus 4 to 6.
Do you agree with him? Is it better to break the integral into 3 parts? Because it's a piecewise function. It's much easier to integrate it, right? Because what's wrong with considering the interval from 0 to 6?
There's multiple different functions.
Yeah, you cannot write a single function inside the integral for that, okay? But if you break it, then the integration becomes very easy. So let's break the interval into 3 different intervals. First, I consider from 0 to 2. Okay, we know that qt is equal to integral from 0 to t I t prime dt prime plus q of 0. Do you agree with the equation? The only thing that I changed compared to the original equation is that I replaced t0 by 0 because I know it is 0. It's equal to from 0 to t. What is it prime in this interval?
Negative 4.
-4. And what is q0? 0. Tell me what's the integral? Do you agree with this? Negative, let me remove that a, I think it's confusing. Do you agree with this? Any problem with that? I just took the integral. -40. Any problem with this? Was there any other way to do this integral? Some students prefer the second one that I'm about to do. So instead of writing qt, I'm going to write q2. Then I'm going to integrate from 0 to 2. it prime dt prime, let me write it here, or plus q0, which is integral from 0 to 2, -4 dt prime plus 0, -4 t prime from 0 to 2, and it's equal to -8 coulomb. What's the difference between these two? Can someone tell? What's the difference between these two methods?
You just replaced T with 2.
Okay. What is -4t and what is -8? What is -4t? It's the formula for
The area from 0 to 2 seconds.
to t seconds, right? Not 2 seconds, t seconds. So that's the equation of charge between 0 and 2. How about -8? That's the final point of the interval. Which one do you prefer? Which one? The second one, because it's easier? Yeah, fair enough. When doesn't it work? The second one. Don't forget the statement of the problem. We want to find qt for positive time. Technically, we want to plot it. So if we go with the second one, can we plot or no? In this specific case, yes, we can. Because we have the starting point, we have the final point, just connect them. That's easy. Because we know it's a line. What if it is a curve? How do you know how to connect those 2 points together? Right? So the first method is the more general way, because you find the function and you can easily later plot it. The second one is just finding a specific point at the end of the interval. So you have the end of the interval, you have the start. And if you don't know how the function behaves, then you don't know how to connect them together. Okay, am I making sense to everyone? Okay, so it's up to you. Many students prefer the second one if everything is linear, if everything involved is a line. Okay. So that's the first interval. The second interval is t between 2 and 4. Q of t. Tell me, what should I write as the bounds of integral? 2 to 4 or 2 to t, right? I'm going to use the general method because that's more difficult, and you can easily plug the value that you want. I t prime dt prime plus q of 2. Remember, the end point of the first interval is the starting point of the second interval. Integral from 2 to t. What's the value of the function between 2 and 4? 2, right? Plus, what's q of 2? Negative 8. It's equal to 2t prime from 2 to 4 minus 8. 2 to t. So it's going to be 2t minus 4 minus 8, right? That's the equation. If you had chosen to go for the integral from 2 to 4, you would have got negative 4. Just plug in the value of 4 here. It's 8 minus 12, which becomes negative 4. So I'm going to write that here. Q of 4 is negative 4 coulomb. Any problem so far? No? One question. Do I need this value or not?
Yes.
For?
It's qt naught for the next equation.
It's the initial value for the next interval. So always you have to find the final value of any interval. So let's go for the next one, which is between 4 and 6. Q of t is equal to integral from 4 to 6 and it prime dt prime plus q4. I wanted to go for t. And 4 to t. What's the value? 6. 6 dt prime plus negative 4. It's equal to 6t prime from 4 to t minus 4, and it's equal to 6t minus 28. No. Yeah? Yeah, minus 2. Let's find Q6. It's 8, right? What is the next interval? Do we have any other interval or no? We do. T greater than 6, right? Integral from 6 to t, I t prime dt prime plus q6 is equal to, what's the value of the function after 6 seconds?
0.
0. Right? So after 6 seconds, q is not a function of time, it's constant, which makes sense because current is 0. So let's plot this. At 0 is 0. Between 0 and 2 is negative 4t. Right? And between 2 and 4, it goes from negative 8 to negative 4. Then it comes up to 8. And what happens after that? Constant. So that is negative 8, negative 4, and positive 8. 1, 2, 3, 4, 5, 6. Now, do you see what I meant by connecting the points? If it is a line, it's very easy to connect them. But if it is, for some reason, a curve, then it wouldn't be that easy to connect. Any question, any issue, problems for this example? Okay. We talked about current having direction. Now, what is the direction of current? Is the light in the room, is it helping you sleep better? Do you want me to just brighten up a little bit? No? It's fine? Okay, what's the direction of the current? A circuit is given to us, and we want to analyze the circuit. This is what we do in this quarter. How can we know what direction of current we should apply to the circuit?
From the positive voltage source to the negative?
But if it is not a voltage source, if it is it's a very big circuit, some resistor in the middle of the circuit, how do you know which direction current is passing? You don't need to know. You just assume one direction. You have two options, right? If you consider any elements, either it can go from one terminal to the other because you have a two-terminal device, or from the other terminal to the first. So you have only two options. What's going to happen if you chose the direction wrong? You're going to get the negative answer for the current, okay? So it's perfectly acceptable and known. You don't need to know the actual physical direction of current. You only need to consider one direction as a convention, as a reference, and then work with it. For example, what can you say about IC and I prime C in this circuit? They have the same value, only with a negative sign, right? IC is equal to negative I prime C. That's the whole thing you want to know, or I need you to know about direction of current. Whatever direction you choose, it doesn't matter. Okay, we talked about current, and now let's talk about voltage. Now, you're familiar with the idea of potential difference, right? Can you give me an example? You must have passed physics 201, right? Do they introduce potential difference in that course for you? Okay. So can you give me an example to show me what's potential difference?
The difference in voltage between...
No, potential difference. Not about electrical engineering, about movements, about objects. Like, okay, for example, let me ask you this. What is the potential energy of this guy?
Zero.
Seriously? No? You probably took it for kinetic energy, right? Kinetic energy is zero. But what is the potential energy of this guy? You shouldn't answer my question. You should ask me a question first. What is that question that you should be asking now? Sorry? Perfect. With reference to what? Relative to what? Okay? That's the whole idea. I promise you, not understanding this is a source of 90% of your problems on exams. You forget that potential is a relative quantity, whether it is for mechanics and statics or it is for electrical. So I want you to remember that potential energy is a relative constant, is a relative quantity, okay? The same goes for potential difference, okay? Electric potential difference. What is the other name for potential difference in electrical engineering? Voltage, okay? So the voltage, from now on, I want you to remember this. The other name for voltage is potential difference. And the difference, the word difference, tell you everything, right? It should be with respect to some reference, relative to some reference. Okay, that's an important part. Now, You probably remember this equation from some physics courses, that work or energy is equal to the charge multiplied by the potential difference. I mean, this is not something that we spend time on it in this course, but I want you to remember that. Put it this way, I want you to memorize that if you don't exactly know what's that about. From your previous courses, you must have seen this. Charge multiplied by potential difference, it's the work or energy. I'm going to talk a little bit about that. The equation here, the line integral, definitely is not going to be part of your exam, because line integration, I mean, I shouldn't expect you to do it for this course. Have you learned line integration in any course? No? Okay. Then forget about this. What's the units of voltage? Volts. You all know it, okay? Can you give me another units for volts? Sorry? Give me another unit for voltage. Instead of volts, what can I do? Look at the equation. What's the units of the left-hand side? Joules, energy, or work, right? And what's the units of Q? Coulomb. What's the units of V then? Joules per Coulomb. Okay. Okay, so the first very important concept or thing I want you to remember about voltage is that voltage is a relative quantity. If you ever forget that, remember the other name of voltage, which is potential difference. Okay, you always have to have a reference. Now, let's talk about, for example, these 2 points, okay? Point A and B. Every 2 point that you choose, whether it's on a circuit or anywhere in this room, you can define a voltage between them, because voltage is just a potential difference. For example, I can define the potential energy of this tape with respect to any points. With respect to floor, with respect to here, with respect to the ceiling, right? So similarly, any 2 points can be defined a voltage. Now, okay, here I have 2 points A and B, and I've assumed that the voltage between B and A, or the voltage of B minus A, is 4 volts. And I've set my reference as point A. Common sense dictates that we set a number for our reference. What number do we usually choose for reference? 0, right? You don't use a square root of 2. You can. You're welcome to use it. I mean, I will doubt some facts about your brain, but I mean, you are welcome to do that. So let's set the reference as 0. So if this reference is 0, what's the voltage at point B? Do you agree that it's 4? Why? Because we need a number that is 4 volts more than the reference. What is your reference? 0. That point should be 4 volts more based on the left part. So it should be 4 volts. Let's look at the right-hand side. What is your reference again? 0. We set the reference to 0. So what is the voltage of point A? Negative 4. Okay? So depending on which point you choose as your reference, the voltage across points is going to be different every point. For example, when I say that the voltage coming out of this outlet is 120 volts, it's measured with respect to a reference. When I say the voltage on this, for example, is 2 volts, and this item is 2 volts, it should be measured with respect to a reference. Am I making sense to everyone? Okay? So, for example, we set VA equal to 0, and we set VB, and VB should be 4 volts. Or here VA should be 0. Sorry, VB. VB should be 0, and VA then is negative 4 volts. Okay. Very important discussion about voltage and current. Let's give you the example for this piece of tape that I'm holding above ground. Now, how much work should I do, or how much energy should I consume in order to move this to the floor? How much work should I do? Nothing, right? I don't want to spend any energy. I don't do any work, okay? It doesn't need any work to be done because it naturally is attracted to go to the zero potential, right? That's one of the laws of physics. The equilibrium dictates that it prefers to go to the zero potential. But what if I want to take it higher? I should do some work, right? I should spend some energy. Now let's talk about a circuit. Look at this piece of circuit, okay? I know it's not a circuit because it's not closed, but you can imagine that the rest of the circuit is not shown, okay? So point B has some negative voltage compared to point A, meaning that point A has a higher voltage. Am I making sense to everyone? For example, 10 volts, meaning that, for example, if you consider B has a zero potential, then A is 10 volts. Now, current is movement of positive charge or negative charge, the direction of current. Positive for historical reason, right? So I have a question. If I want to move positive charge from left to right, from A to B, should I do work or it is naturally attracted? You know that, right? If I want to move positive charge from left to right, it's naturally attracted. You don't need to do anything. So you don't need to do any work. So positive charge is by nature attracted to the negative terminal. So no work should be done on the charge. In fact, just give me one moment and I will get back to you. In fact, since charge is moving to the right, look at the tape again. If I leave the tape, what's going to happen to its potential energy? It's going to lose it, right? Because it used to have some potential energy with respect to the floor. Now it doesn't, because it's on the floor. The same thing happens to the positive charge. If the positive charge is going to the right, it's going to lose potential energy. It's going to lose energy. And where does that energy go? It is absorbed by the element that is between point A and B. So the current moves in that direction. The energy that the charge loses is going to be absorbed by the element. What was your question?
In this example, for example, like how you were saying that point B you could say has a voltage of 0, and point A has a voltage of 10. How would just a single point have a voltage if the unit is a difference between two things?
Unless you introduced some reference, it doesn't. Yeah, so perfect question. I said B is 0, A is 10, right? That's one of different possibilities just for mathematical ease. In fact, you don't know exactly what the voltage of B is, what the voltage of A is. You could consider B being pi volts and A 10 plus pi volts. But for the reasons that I talked about, it's easier to set the reference as 0. Okay? But you're right. You cannot assign a single point, at least not in this course, unless you have a reference. Okay. Very similarly, the opposite case. What if I switch the voltage, like the left one has a higher voltage? Did I change the point? No, the left one had the higher voltage. Now let's assume the right one has a higher voltage. Point B is 10, point A is 0. So what happens if I want to move the positive charge from left to right? It's not attracted by nature, it's repelled, right? So what should be done? There should be some energy or work done on the charge. Where does that energy come from? From the element between them, okay? There should be some element that can provide this energy. So the charge can be moved from A to B. Otherwise, it won't, okay? That is the basic idea behind this. If the current enters from the positive terminal of the voltage and passes through the element, energy is absorbed by the element. If the current enters from the negative terminal and leaves from the positive terminal, then energy is supplied by the element. From the way I'm representing this in your lecture note, you should guess that this is pretty important, okay? Now, much more important than energy in electrical engineering is something very closely related to energy. Do you know what that is? You usually see that on every electrical appliance. You don't see energy on electrical appliance. What do you see on light bulbs, for example? Power. You see 100 watts, 20 watts, 10 watts, 1 kilowatt, okay? So let's define power and talk a little bit about power. So power is just the rate of change of energy with respect to time, dW over dt. That's the basic definition of power. I want you to remember that. For example, if you have a function of W, or energy, how do you find power? Take the time derivative, right? But with the simple proof that I've brought here, you can study that. Just a line, just one line of proof. This is one of the most important equations in this course. This is the one of the fundamental equations. Power is equal to voltage multiplied by current. voltage multiplied by current. But based on the discussion that we just have about potential, we can talk about two different kinds of power. One is the supplied power, one is the absorbed power. This is something, and I want you to memorize for all three exams. In fact, I want you to just have this in front of you when you're doing homework or you're doing in-class assignments. Okay? If the current enters from the positive terminal, we actually discussed this, we proved this. If the current enters from the positive terminal, you multiply I and V, and that will give you the power absorbed by the element. If the current enters from the negative terminal, you multiply I and V, and it will give you the supplied power. Okay? If you're confused, it means that you're normal. This is a confusing topic, especially in the first few lectures. We'll try to do as many examples as we can to just clear that confusion. But I want you to memorize this. If the current enters from the positive terminal of the voltage, it means that if you multiply I and V, it will give you the absorbed power. The other way, it will give you the supplied power. Okay? Let me ask you a very probably simple question, and then I move to the next topic. I have some electrical appliance, and it's absorbing 10 watts of power. It is absorbing 10 watts of power. What's the supplied power by that element? Is it obvious? So the supplied power is negative of absorbed power. So when you see negative in the expression or in the number associated with the power, it doesn't mean that it's bad or good. Okay? It only means that whatever you had initially in mind, it's not doing that. For example, if you're talking about absorbed power and get a negative number, it means that that guy is not absorbing power. It's actually delivering, supplying power. Or the other way. If you're talking about supplied power, for example, you're talking about some projector, okay? And you want to calculate its supplied power, and you get negative 100 watts. What does it mean? It means that it's not supplying power, it's absorbing 100 power, but it's not supplying, okay? So remember, these are negative of each other. So let's do an example. I hope that clears everything. Okay. Calculate the power absorbed by these elements, each one. Let's start with element A. Give me some suggestions. I want to calculate the absorbed power by element A. What should you do first? Which one the question is asking you? Absorbed, right? Print this page, cut across it, and just, I don't know, glue it into your laptop or whatever, okay? Just remember this, however you can. So this one, look at it. Which case gives me the absorbed power? When the current enters the positive terminal. Do you agree with that? So let's go for element A. Is the current entering the positive terminal? No. What do you suggest? This is the part that's confusing, and I want you to pay attention. So what should I do? There are tens of ways to do it. Not tens of, 2 or 3 ways to do it. But I want you to tell me, what would you choose? I want you to calculate the absorbed power of A. How do you deal with this? Pardon me? Perfect. Do you agree that the current is entering negative terminal? So, this is my question. If I multiply 2 by 2, what kind of power I found? Supply power. So, what do you do to that to make it absorb? Add a negative sign. That's it. Negative 4 watts. What's the other way to do it? I want you to pick whatever you're more comfortable with.
The current, because negative current is the same the other direction.
Perfect. Can you tell me what is the red current? What's the value of red current? Negative 2. Okay, now the red current is entering from positive terminal. So if I multiply those two numbers together, what kind of power it will give me? Absorb. So let's multiply them. What should I multiply? 2 by negative 2. That's the confusing part. See? Sir, what was your name? What was your name? Reed. Reed mentioned to go for the supplied one and then add a negative sign. Okay? Remember, this negative sign, where is it coming from? It's coming from the fact that supplied and absorbed are different. Okay? But when we did with the red thing, there is also a negative sign. But that negative sign is inside the number that is associated with current. Okay? I want you to be able to recognize this difference. When I'm talking about current entering voltage in the previous page, see, current entering from the positive terminal of voltage, do I care what is the value of I and V? No. I only care about multiplying I and V, whatever value they have. They might be both positive, they might be both negative, whatever. If you multiply I and V in this way, when current is entering the positive terminal, the value is absorbed. The value that you find is absorbed. So for this case, let's not look at the values. The current is entering, the black current is entering from the negative terminal. What does it mean? If I multiply the associated numbers, what kind of power it will give me? Supply. How do you find the absorbed from that? Add a negative sign. Did that make sense? So if there is some confusion, it's normal. The only thing that you can do to decrease that confusion is just do more examples. So, what is the power absorbed by element A? So I hope that is clear how to okay? I'm going to write it like this as well, and I hope after talking so much about this, it makes sense what I mean by that. Does it make sense to everyone? The negative sign can be either from changing the supply to absorb or for the current itself. And it's equal to negative 4 watts. Okay. For element B, someone else, please.
The current remains constant, so we just use the same current.
Yes. So you agree that this current is negative 2 amps, right? Why the current is the same?
Because the line doesn't branch out, it's the same.
Perfect. It doesn't have anywhere else to go. So all of it must come down. So how can you find the absorbed power of element B? The red current, is it entering from the positive terminal? Okay, so if I multiply the red and the voltage, what kind of power it will give me? Absorbed. That's what I want, right? So what is the red current? What is the voltage? Negative 16 watts. Someone else do the part C for me, please. Yep.
It's going to be 10 volts because 10 volts across element B and sister in parallel will be the same voltage across both.
Do you agree with him? That's very important point in your learning for this course. He just mentioned that B and A have the same current. Do you agree that B and A are in series? So series elements have the same current. What just he mentioned, Isaiah, he said that D and C are in parallel. So what do they share? What quantity they share? Voltage. So if the voltage across D is 10, it means that the voltage across C is also 10 volts. So how do you find the absorbed power? Negative 4 amps times 10 volts. Anyone having a problem with what he said? What is the first negative sign for? Because the current is entering from the negative terminal, so if you multiply those two numbers, it will give you the supply power. So you need a negative sign to change it to absorb. What is the negative inside the first parenthesis for? That's the value of the current. That's the value of the current. Okay? So what is it? 40 watts. And finally, PD absorbed. We need the negative sign again, right? But here we have a positive current and 10 volts. Negative 20 watts. Any problem? Do you feel the confusion is little by little going away? Okay, if not completely. What is the sum of the absorbed power by all elements? Why? Does that tell you something? A very fundamental law in physics. Sorry? What is that called? Conservation of energy, right? Whatever. Well, let me ask another question before moving to the next part. Which element is actually supplying power? C, right? Because its absorbed power is negative. It means that it's actually supplying. Sorry, I said it the opposite way. Did we calculate absorbed or supplied? Okay, so let me ask my question again. Which element is actually supplying power? A, B, and D. Which element is actually absorbing power? C, right? When absorbed power is positive, it means that it is actually physically absorbing. When it is negative, it means that it's not absorbing. It's, on the other hand, is supplying, right? Did that make sense to everyone? Okay, so if you add all of them together, it's gonna give you PA plus PB plus PC plus is equal to 0. Okay. We have voltage sources and current sources. These are called ideal voltage sources and ideal current sources, or sometimes we call them independent voltage source, independent current source. Why do we say independent? Let's look at, for example, the current source here. You see a circle, and inside the circle there is an arrow in one direction. What does it mean if I write 2 amps besides that element, besides that symbol? It means that no matter what voltage is applied across this element, or no matter what the rest of the circuit is, this branch that this element is part of will always have a current equal to 2 amps. That's called independent. It's independent from the rest of the circuit. Okay? So that is a current source. How about voltage source? Voltage source has different symbols. I mean, pick any one. What does it mean if I write 4 volts besides that circle? It means that no matter what the rest of the circuit is, or no matter what the rest of the circuit is doing, what kind of current or voltage is applied to the rest of the circuit, the voltage across these 2 points, or the potential difference between these 2 points, is always 4 volts, meaning that the positive terminal is always 4 volts higher than the negative terminal. So for example, if your negative terminal somehow ends up being 8, you are sure that the positive terminal is 12. Always. The 4 stays constant. So independent sources. Any problem with them? Okay. With everything easy that we learned, there should be something painful as well, right? So we have independent sources, and now we have dependent sources. What does it mean? It means that they behave the same as usual sources in the sense that they provide current and voltage to one branch or 2 points, but they are dependent on some quantity in some other points of the circuit. For example, let me talk about this example just a little bit, and then I will be back to the notes. Look at this diamond shape. Okay, do you see that? First of all, I want you to tell me, is this a voltage source or a current source? The diamond one. So how do you know it's a voltage source? Plus and minus. Remember, voltage is plus and minus. Current has a direction, has an arrow. So that's a voltage source. What's the value of it? Is it like 5 volts? Is it 3 volts? No. It depends on some other variable across the circuit, in the circuit. For example, what does it depend on? It depends on VB. Where is VB exactly? Across the element B. So if you find the voltage across element B, multiplied by 3, it will give you the voltage across the voltage source. That's why we call it dependent. Did that make sense? Okay. So, how many types of dependent source we have? 4. You can see the name, voltage controlled voltage source, current controlled voltage source, current controlled current source, and voltage controlled current source. And these are just the abbreviations. Look at the two to the left. What kind of a source is this? Voltage source. This is the important part I want you to follow. Okay? These two are voltage source. How can I say? How can I tell? Plus and minus, as easy as that. Okay? So what's the difference between them? One of them depends on some voltage in the circuit. The other one depends on some current in the circuit. That's the only difference. But both of them are voltage sources. Okay? So this is a pretty maybe difficult question, but if you can answer it, it means that you're safe, at least for this part. What is the units of K?
Unitless?
What is the units of R? You don't.
Also unitless?
Is it unitless? What is it?
Yeah.
Volts per amp? Do you agree with him? Let me, you're correct, but let me ask you this. What should be the unit of the whole red thing?
Volts.
Why?
Is the volts.
Because that's a voltage source. So the whole thing should be volts. What's the units of that IX part? Amps. So what's the units of R? Volt per amps. What do you call volt per amps? Oh. You know that, right? Omega. Oh. Resistance. So, but I don't write it as ohm, I just write it as volt per amps. Again, what's the units of this guy? Volts, right? What's the units of K then? Volt per volt or unitless. What's the units of this whole thing? Amps. Then what's the units of K? Amps per volts. No, sorry. It's amps per amps. Correct me if I'm wrong, okay? Unitless. So this is amps. What's the units of G? Amps per volts. Did that make sense to everyone? Okay. Let's do our last example. Find VB and VC. And in the dependent source, what is the units of 3? Okay. We don't know any systematic way of handling circuits, not until lecture 4 or 5. Okay? So we have to be creative. We have to rely on the only things that we know. What should we do?
Voltage is the same between parallel elements, so VC equals 3VB.
Yeah. That's good. Do you agree with him? These two elements to the right are in parallel, so VC should be 3VB. Yeah. But what is VB? Let me ask you one thing. What does that 4 volts mean? Huh? It's independent. So if you want to explain that to me, what does that 4 that I've written mean? 4 volts, what does it mean? No matter what happens to the rest of the circuit, the top terminal is 4 volts higher than the bottom terminal. Do you agree with that? Okay. So that's a good starting point. Can I just set some reference for my circuit? Will that be a problem if I set a reference? No. What do you call a reference in an electrical circuit?
Ground.
Ground, right?
I should have said earth.
This is ground. What's the voltage associated with ground? Reference, 0. Okay, I'm going to set that point as 0. Can you tell me if that is 0, what is the top terminal equal to? Everyone, 4. Do you all see that? If the top terminal is 4, move to the right after element A. What is that point? She's saying 2. Do you agree with that? Someone else explain why.
Because it goes from positive to negative instead of negative to positive, so you have to subtract it.
Yeah, so what is the meaning of that 2 volts across element A with that positive and negative sign? What's the meaning of that? It means that the left terminal should be 2 volts higher than right terminal, right? The left terminal is 4 volts, so the right terminal must be 2 volts. Now, can someone tell me what is VB? Why 2? Perfect. Okay, this is one of the most common mistakes in this course. Students see the positive terminal, whatever value is that, they say VB is equal to 2. But based on his explanation, what was the first thing that he paid attention to? Is that the negative terminal is grounded. So VB, this is how I would write it. VB is equal to 2 volts minus 0 volts, ground. If the negative terminal was 3 volts, then what would VB be? Negative 1, okay? Did that make sense to everyone? So VB is 2V. What can you say about this value here? 6 volts, because it's just 3 VB. And based on that, what is VC? Last question. What's the units of 3? Unitless. It's changing volt to volt, so it's unitless. You're going to do your mini lab. I'm going to eat my popcorn, okay? Any question? By the way, don't worry. This is one of the probably the longest lectures that we have. I mean, I think there is only one longer than this. So if you don't have time for in-class assignment today, it's not like every lecture, okay? This is a pretty long lecture.